Okay, so when we're working with redox reactions, first of all, you might wonder whether a reaction is a redox reaction or not. So it would be very helpful to be able to determine whether a reaction is redox or not. So under identifying redox reactions, there's really one easy way to tell whether a reaction is redox, and that is if the reaction involves any free element or more than one free element, then it's definitely redox. And it doesn't really even matter whether the free element is a reactant or a product. If there's a free element involved in the reaction anywhere, it's redox. That's really about the only absolute criteria there is. The only other way to determine whether a reaction is redox or not is to determine the oxidation state of each atom of each element in the reactants and the products and see if anything changes. And it can be kind of a tedious process in some reactions, but it's basically what you got to do to make sure. If you determine the oxidation state of each atom of each element in the reactants and the products and nothing changes, that is, if all of the oxidation states end up the same as they started out, then it's not redox. On the other hand, if one of the oxidation states goes up and another one goes down, that's redox. Because an oxidation state going up is another word for oxidation. And an oxidation state going down is another word for reduction. In fact, that's kind of one of the easy ways of remembering what oxidation and reduction are. Reduction is a reduction in oxidation state. So if the oxidation state goes down, that means you've gained electrons, and that's a reduction. Okay, so if one goes up and one goes down, that's redox. If there's any other situation, you probably did something wrong. So you'd want to double check. Because, for instance, if you get one oxidation state going up, but nothing going down, that's not really going to happen. Or if you get, say, two things going up and one thing going down, well, that's possible, but you're not likely to see anything like that in general chemistry. So again, double check. Basically, what you want to see is either no changes at all or one going up and one going down, one or the other. And some examples of things that might be redox or not redox would be, say, for example, HCl and NaOH will produce NaCl and H2O. If we assign oxidation states to each atom of each element on both sides of the equation, and then compare products to reactants and see if any of the oxidation states change, then we can see whether this is redox or not. Okay, and HCl, we know that Hydrogen with a nonmetal like chlorine is always going to be +1, and chlorine with anything that's less electronegative, like hydrogen, will always be -1. Sodium will always be +1 in its compounds. Hydrogen will always be +1 when it's with nonmetals like oxygen. And oxygen, when it's with a nonmetal that's less electronegative than itself, will be -2. Sodium, again, always +1. Chlorine, when it's with a metal, will always be -1. Hydrogen, when it's with another nonmetal like oxygen, will always be +1. And notice I'm writing just +1 even though there are two hydrogens, because each hydrogen atom is +1. You want to find the charge on each atom of each element, regardless of how many there are, just so that you're comparing things on a level playing field from one side of the reaction to the other. If you find the collective charge on all of the atoms of that element, that could actually change depending on how the atoms of that element are grouped on one side of the equation versus the other. Notice over here on the left-hand side, the two hydrogens are separate from each other versus the right-hand side where they're both together. You could, if you find the collective charge on all of the hydrogens, you could end up thinking that the charge on the hydrogens changed when it really didn't. So you want to write down the charge on each atom of each element. So the hydrogens are +1 each, and the oxygen is -2, like it is always with every element except fluorine. So looking at the two sides, you've got hydrogen starts out at +1, ends up at +1. Chlorine ends up at -1, ends up at -1. Sorry. Sodium starts out at +1, ends up at +1. Oxygen starts out at -2, ends up at -2, and the hydrogen goes from +1 to +1, no changes. So that is not a redox reaction. And in fact, this is an acid-base reaction. We've seen it before, actually. It's also known as a double displacement type reaction because the positive and negative ions of the reactants switch partners, essentially. And acid-base and double displacement reactions are generally not redox. And so it worked out. Let's see, on the other hand, if we have two sodiums plus two H2Os reacting to form 2NaOH and H2. Now, actually, what we've said above here, any reaction that involves free elements will definitely be redox. Notice what we've got here. We've got sodium on the left-hand side. That's a free element. We've got hydrogen on the right-hand side. That's a free element. So right away, we know for sure this is a redox reaction. But if we want to prove it, we can find the oxidation states of each atom of each element. Sodium on the reactant side is a free element, so that has 0 charge on it. In H2O, we have hydrogen with another nonmetal, so each hydrogen will be +1, and oxygen will be -2 with everything except fluorine. So that was easy enough. For the sodium hydroxide, again, sodium is always +1. Oxygen is always -2 with everything except fluorine. Hydrogen is always +1 when it's attached to a nonmetal like oxygen. And so we have that. And then we have the free element hydrogen, which is 0 as charge. So we've got sodium starting out at 0 and ending up at +1. In order for sodium to go from 0 to +1, that means that sodium must have lost 1 electron. Losing an electron is oxidation. Okay, so there's your oxidation right there. And let's see, hydrogen goes from +1 to +1 and, oops, 0. So one of those hydrogens goes from +1 to 0, or sorry, two of them go from +1 to 0. That's a reduction. Notice that some of the hydrogens go from +1 to +1, so some of the hydrogens stay the same, but some of the hydrogens are reduced. And that's all it takes. So we've got two hydrogens starting out with +1 charge. They gain 2 electrons. Oops, and sorry, that's 2 sodiums and 2 electrons. Okay, so the 2 hydrogens gain 2 electrons and become H2 with 0 charge. That's reduction. So it is definitely an oxidation reduction. Notice also that the sodiums, there are 2 sodiums, each of them loses 1 electron, but there are 2 of them, so that's a total of 2 electrons being lost by sodium and a total of 2 electrons being gained by hydrogen. In fact, those are the same 2 electrons. So again, this is a reason why oxidation and reduction always occur together. It's because hydrogen cannot take in those 2 electrons until sodium gives them up. Sodium's not going to give them up until something like hydrogen is there ready to take them in. And so it's the same electrons that are causing the oxidation and the reduction. Okay, and you can look at some more examples of things like that, but they're basically, tracing out the same path. Find the oxidation state for each atom of each element and see if it changes or not when you get to the products. And that way you can find if it's an oxidation or reduction. Now for something that I kind of wish they had never thought of, the concept of an oxidizing agent. An agent is something that does something. So an oxidizing agent is something that causes oxidation. But it causes oxidation in something else. So the oxidizing agent is not actually oxidized, it's reduced. Because the oxidizing agent causes oxidation in something else by taking electrons away from it. So the oxidizing agent causes oxidation in something else by taking electrons away from it, because a loss of electrons is oxidation. So the other thing is losing electrons, so the other thing is being oxidized. The oxidizing agent causes that oxidation by taking in those electrons. But when the oxidizing agent takes in those electrons, the oxidizing agent is actually reduced. Okay, so it kind of goes around and around, and it can be hard to figure out. Probably the easiest way to remember it is just that the word agent turns things around. The oxidizing agent is the stuff that's reduced. And the reducing agent is the stuff that's oxidized. The reducing agent causes reduction in something else. By donating electrons to it. And by giving away electrons, the reducing agent is actually oxidized. So again, just think of it as the word agent turning things around. The reducing agent is the stuff that's oxidized. The oxidizing agent is the stuff that's reduced. And so we can look at some examples of that also. Okay, so in the following examples, first of all, we want to determine whether the reaction is redox or not. And if it is redox, name the oxidizing and reducing agents. Okay, in the case of lithium and chlorine producing lithium chloride, this is pretty easy and straightforward because, like I said, any reaction that involves free elements is redox. Lithium is a free element, chlorine is a free element, so this is definitely redox. We can prove it, though, by noting the fact that a free element like lithium has 0 oxidation state, and the same for the free element chlorine. But in lithium chloride, lithium takes a charge of +1, and chlorine takes a charge of -1. So lithium +1 is an oxidation, and chlorine 0 to chlorine -1 is a reduction. In this reaction, lithium, that is the element lithium, is the element oxidized. And that means it's the reducing agent. Chlorine, the element, is the element reduced, and that means that it's the oxidizing agent. So the oxidizing agent or reducing agent, they'll always be the reactants. And usually we're looking for a specific element or the compound in which the element is found. That's the reducing agent or the oxidizing agent. Another one could be aluminum plus tin ions will result in aluminum ions and tin. Well, again, we've got free elements here, aluminum and tin on opposite sides, but anything with free elements is definitely redox. So aluminum starts out at 0, ends up at +3. That's an oxidation. Tin starts out at +2, ends up at 0. That's a reduction. Aluminum, the element, on the reactant side, is the element oxidized. And that makes it the reducing agent. And the tin ions on the reactant side will be the element reduced, and that makes it the oxidizing agent. Okay, and so on. There's also the example of combustion reactions. As I mentioned before, combustion reactions are always redox reactions. Because, for one thing, combustion is a reaction with oxygen. Oxygen is a free element, and like I said, any reaction that involves a free element is definitely redox. And also a reaction with oxygen is an oxidation. And if there's an oxidation going on, there has to be a reduction going on also. In the case of combustion reactions, carbon becomes carbon dioxide, ideally, and hydrogen becomes water vapor. An example would be, say, the combustion of methane. That's the principal ingredient in natural gas. And when you burn methane in air, it combines with 2 oxygen molecules from the air, and it produces CO2 and 2 H2O. Oxygen, again, is a free element, so this is definitely redox. We have, let's see, oxygen with 0 oxidation state going to oxygen in the products, which in any compound, oxygen will have a charge of -2, except with fluorine. And so oxygen 0 going to oxygen -2 would be a reduction. And let's see what's oxidized here. We've got CH4, which has 0 charge. Carbon will be +1 each, as it is with any other nonmetal, like carbon. There are 4 carbons, so that's +4 for, or sorry, there are 4 hydrogens, so that's +4 for the 4 hydrogens. And there's 1 carbon to bring that back down to 0, so carbon must be -4 here. And let's see, over here we've got CO2 with 0 charge overall because it's a compound. Each oxygen is -2. Each, there are 2 oxygens, so that's -4 for the oxygens in CO2. The carbon itself alone has to bring that up to 0, so carbon is again +4. And in the in the water, it has 0 charge overall, being a compound. Each the oxygen has -2 charge, and hydrogen will be +1 as it is with any other nonmetal like oxygen. And so let's see, we've got carbon going from -4 to +4. And there's your oxidation. So carbon is oxidized, oxygen is reduced. So it is definitely redox. And sometimes with some of the other hydrocarbons like propane or butane, figuring out the oxidation state on the carbon can be difficult. Sometimes you end up with fractional numbers for the oxidation states of carbon in compounds like that. It's just one of the many weird things about organic chemistry. So we don't tend to use too many examples like that. But it is definitely oxidation reduction. Okay, well that actually brings us to the end of chapter 4. According to the schedule, we're going to skip chapter 5. That'll come back in Chem 121. And we're going to go, and actually we're going to skip 6 also and go right on to chapter 7. But we're close enough to the end in this lecture that I think I'm going to pick up chapter 7 in the next lecture. So see you then.